Now that we've seen how we can make alcohols from organometallic reagents, in this video we're going to look at how we can oxidize those alcohols. And we're going to start with primary alcohols and see that we can oxidize primary alcohols to either aldehydes or carboxylic acids. So notice we have already seen that we can take an aldehyde and reduce it to a primary alcohol. Now we're going to see that we could take a primary alcohol and oxidize it to an aldehyde. Make sure you keep reagents straight. What is an oxidizing agent? What is a reducing agent? That will become very important to you, especially when we're doing retrosynthesis, because we can go, we know we can go from an alcohol to an aldehyde and vice versa. And so you have to keep things straight. So what are the reagents for oxidation? Here I have taking a primary alcohol and reacting with chromium trioxide, and you produce an aldehyde. So this is a great way of making aldehydes, right? And the mechanism of this is fairly straightforward. Chromium trioxide is a Lewis acid. The alcohol is a Lewis base. It donates a pair of electrons to the chromium, breaking that chromium-oxygen double bond. And the result is a Lewis acid-base complex conjugate, similar to what we've seen when we talked about electrophilic aromatic substitution reactions. However, the next step is a simple proton transfer. So these types of reactions are usually run in pyridine, and pyridine is a weak base. And so we could use pyridine to deprotonate the alkyl oxonium ion, generating a pyridinium ion, and then the pyridinium ion can then protonate the chromate, the right part, right, the oxygen with the negative charge on it, and the result is a neutral compound that looks like this. However, it's fairly acidic in that that chromium is still trying to withdraw electron density away from the oxygen, and so again we still have pyridine present, right? And that pyridine can remove one of the hydrogens coming off of the carbon. When it removes that proton, the pair of electrons from that carbon-oxygen bond then go to form a new carbon, or from the carbon-hydrogen bond, go to form a carbon-oxygen double bond. And when that carbon-oxygen double bond starts to form, we break that oxygen-chromium bond and the electrons go to the chromium. This produces our aldehyde, right? And of course it also produces a pyridinium chromate salt, which we'll see something very similar to this in just a little bit being used again as an oxidizing agent. Now if I take again a primary alcohol and instead treat it with sodium dichromate in sulfuric acid and water with heat, I can generate a carboxylic acid. So notice now I am oxidizing it completely to a carboxylic acid, oxidizing that primary carbon to a carboxylic acid. And the way that this works is oxidation is going to take place to produce an aldehyde. That aldehyde, in the presence of water, as we remember, forms an equilibrium with the geminal dial. This geminal dial can then be oxidized with the chromium ion to further oxidized to a carboxylic acid. And we see the key is water, right? In the first set of reagents with chromium trioxide in pyridine, water wasn't present, and therefore water couldn't establish that equilibrium to form the gem dial that could then be oxidized further. So we can control oxidation by essentially limiting the access of water to our aldehyde. If we add water to the aldehyde, we get further oxidation to the carboxylic acid. So here's a couple of examples. The first one is taking 1-butanol, reacting with chromium trioxide in pyridine. Remember, no water present, so the alcohol is going to be oxidized to the aldehyde, right? I just generate an aldehyde here. There are other oxidizing agents that we can use, and a common one is PCC in dichloromethane. And it produces the same thing. Notice absence of water, I can take benzyl alcohol and I can produce benzaldehyde from that. So we've already seen that if I take benzaldehyde, I can reduce it to benzyl alcohol. Now we see that I could take benzyl alcohol and oxidize it to benzaldehyde with PCC in dichloromethane. Now you might be saying, what is PCC? It's just a bunch of letters to me. Well, it stands for pyridinium chlorochromate. And it is very similar in structure to the pyridinium chromate salt that we saw. But chemists found out that if you modify that chromate salt to have a chlorochromate salt, that chromium is still can still act as a Lewis acid. The chloride comes off, and now you're kind of generating chromium trichloride in that process. And so again, an easy way of introducing chromium trioxide through the pyridinium chlorochromate salt. This is actually a nice way of doing an oxidation because instead of using pyridine, you're using dichloromethane, which is much easier to remove, and it's a salt that's actually soluble in dichloromethane. So we see a lot of use with PCC in dichloromethane, and students tend to like it too because it's kind of easy to write as a reagent. Okay, so secondary alcohols are oxidized to ketones. And here I have a secondary alcohol. The reagents for this, we're going to see actually we could pretty much use any of the reagents that we've used prior. So I could use chromium trioxide in pyridine, but I could also use PCC in dichloromethane, and I can also use sodium dichromate in sulfuric acid, water, and heat, right? Any of these reagents take a secondary alcohol and oxidize it to a ketone. So notice the carbon-oxygen single bond is now being converted to a carbonyl compound, right? A ketone. And no further oxidation can take place because of the two R groups that are present. So if you have a hydrogen present, you can, in water, you can form the geminal diol. But remember that that ketones are actually relatively stable in water, and that equilibrium is very, very low when it comes to forming the geminal diol. So no further oxidation takes place here. The last type of reagent that we'll see in terms of oxidizing either primary or secondary alcohols is what's called the Swern oxidation. So if you notice up above, all of the reagents for oxidation include chromium. And chromium +6 is a great oxidizing agent, but it's also extremely toxic. So you have to be very careful in terms of disposing any waste that you accumulate in these types of reactions. So not very long ago, another method was developed where you can take a primary or a secondary alcohol. This happens to be a primary alcohol, and you treat it with DMSO, right, dimethyl sulfoxide, and oxalyl chloride. So oxalyl chloride is ClC double bond O, right, so there's a carbonyl, and it's connected to another C double bond O, a carbonyl, which the carbon has a chlorine coming off of it. So this is a diacyl chloride, and it's the simplest diacyl chloride that we can have, oxalyl chloride it's called, in the presence of a base, triethylamine. And the result is the same, right? Primary alcohols get oxidized to aldehydes with the Swern oxidation. Now, if I take a secondary alcohol and treat it with these reagents, the Swern reagents, then I can generate a ketone. So notice there are, you could use chromium trioxide, you could use PCC, or you could use the Swern reagents to oxidize a primary alcohol to an aldehyde, and you can use all of the above to oxidize a secondary alcohol to a ketone. The last oxidation we're going to look at in this section is an oxidative cleavage of a diol, and specifically a vicinal dial. So vicinal dials will react with periodic acid, not periodic acid, it's periodic acid. And periodic acid is HiO4. It's very similar to perchloric acid, HClO4. And the product of this are carbonyl compounds, right? So if I have a vicinal dial, which I know how to make from alkenes, right? If I take alkene, treat it with osmium tetroxide or potassium permanganate, I generate vicinal dials. And then if I treat that vicinal dial with periodic acid, then I can generate carbonyl compounds. So what's going on in this process? The carbon-carbon bond is cleaved, and that each of the carbon-oxygen bonds are converted to carbonyl compounds. So here I have this vicinal dial. Notice if I cleave the carbon-carbon bond, the carbon on the right has a hydrogen coming off of it, so I'm going to get an aldehyde. I'm sorry, the carbon on the left. The carbon on the left between those two carbons has a hydrogen coming off, and I'm going to get an aldehyde. The carbon on the right between the two dials doesn't have a hydrogen. It has a methyl group and an ethyl group coming off, so I'm going to form a ketone. So here I get an aldehyde, and the carbon on the right gives me a ketone. So, this is one way of making aldehydes and ketones kind of indirectly from alkenes, right? Taking an alkene, converting it to a diol, and then oxidatively cleaving it. Of course, we already know another way of forming these carbonyl compounds, and that's the cleavage of the alkene directly using ozone, so ozonolysis. But something else kind of in our arsenal, if we already have a vicinal dial, we can convert it to an aldehyde or a ketone, depending on the R groups, depending on the substituents coming off of it.